We memorize the law of inertia, but many people wonder if the law of inertia is separate, right? Isn't it just something to know in physics? Then how is it applied to problems? There must be people curious about this, right? This represents V0, initial boundary condition. Hello, this is Minsikhem from Minsikhem Academy. Today, let's learn about Newton's first law, the law of inertia, in our concept video. In Chinese, the word for inertia is made up of two characters. The first character means habit, something that you keep on doing. In other words, it signifies the desire to maintain the current state. That's the habit part. And the second character means nature or character. So, to put it simply, you can think of it as a habit you've had. The tendency to keep doing what you were already doing. That is called inertia. Let me give you an example. For instance, students often fall asleep during physics class in university. If you nap slumped over your desk once or twice, at some point that becomes inertia. It's a habit. Because it's not that they can't sleep, but even after getting enough sleep, they get sleepy at that time. Those things have become the body's inertia. It has become a habit. Those are examples of inertia. Another case is you see the picture here. Here I briefly used the Muji character, and Muji is looking at the woman on the canvas, making a face without realizing it, and is about to rush in. But the crocodile, whose name I don't know, is blocking it. These are all inertia. Inertia. So people. There are many types of inertia. People behave differently depending on the time and specific circumstances, right? Because of that, psychology is very difficult. On the other hand, the inertia of an object. I said today you need to know 3 key points of inertia, right? Let's see. To put an object's inertia in a single sentence, it's this. An object at rest stays at rest, and an object in motion stays in motion. In other words, it's the tendency to maintain its current state. You can just think of it as a habit. You don't need to even memorize. It is easy one, right? So it's showing that there's only one inertia for objects. Look here, see this picture. If you look at the picture, this object is currently at rest, right? When it's at V0, it remains at rest. And on the other hand, like on the right side, it moves with velocity. But if no external force acts on it and there's no friction, it continues. So this is inertia. So objects only have this habit of inertia. What did I say about people's habits earlier? Some people drool just at the sight of food. Some people's eyes wander when they see a pretty woman. And some get irritable when they're hungry. Habits are all different, right? Right, but the object, there's only one habit. One. What is at rest stays at rest, and what is moving keeps moving. That's the only habit. Got it? That's why physics is easy. How difficult is it for psychologists? There are so many psychological cases with people, right? So, one characteristic of inertia is that we feel inertia like this. When we're on a bus and it suddenly stops, what happens? We get pushed, right? Because we are trying to keep moving forward, but since the bus stopped, we still have the tendency to keep going, like the bus. But when it suddenly stops with a screech, we get pushed. It's because we had the tendency to keep going. That's why we feel it. They say they felt inertia, and also something we often see in problems is when an airplane loads supplies like this. Then, when you load the supplies and just leave them, what happens? The supplies drop swiftly, but the supplies do not fall vertically like this. Because if it is moving at 100 kilometers per hour, the object is also moving at 100 kilometers per hour like this. So when you drop the object, it is 100 kilometers per hour in this direction. Do you understand? Because it was continuously moving. Then, while moving, it maintains constant speed in this direction, and due to gravity, It accelerates in this direction, resulting in parabolic motion. So, inertia has these characteristics. If you are inside a moving object, you moves at the same speed as the object. But if you are inside a stationary object, you will also be stationary. In other words, you're in the same state as the object. This is the characteristics of inertia. It's very easy. Let's think of another example. Have you ever had a thought like this? Let's imagine a scenario where you have to jump out of a subway or train going 200 kilometers per hour. It's a situation you often see in movies or comics. When you jump, since it's still moving, you might think if you jump, you'll move backward and land here. You might have thought that if you're briefly in the air, but that's not the case, okay? Even if you jump, you land in the same spot. The position doesn't change. Got it? Because you are also moving at 200 kilometers per hour, it means you have inertia. So when you jump, you land right back in the same spot. Now try this on the subway. Try it today, okay? You can experience exactly what I'm saying. All right, next up is the second of 3 key points on inertia. Just because an object has inertia doesn't mean it will always maintain its state. It can change. In other words, there is a way to make stationary object move or to make moving object stop. The only thing that makes this possible is force. When a force is applied, its inertia can change. Sometimes this is called impact. Impact. So, for example, when a pitcher throws a ball like this, a ball, let's say it goes at 140 kilometers per hour, but the batter hits it. What happens when they hit it? What happens when the bat hits the ball? It will fly off in the opposite direction at 200 kilometers per hour, right? The impact after the collision. After the impact, it will fly at 200. So if you plot this on a graph, VT would look like this. Initially, it goes at 140 in this direction. Let's call it Since it's the left side, let's call the left side negative and the right side positive. So as it goes straight at 140, at some point it will collide at time 0. Then what happens? To 200 like this. Let's say this unit is kilometers per hour. It changes like this, like this. But what happens between here is that this interval is very small. We will learn about this interval. Wait, should I draw it again? Here, again, this part here, right? This part is where the collision happened. Collision, right? So the ball, according to the law of inertia, it was moving to the left at 140, and at this moment, time 0, a collision occurred, changing the inertia. It's moving in the opposite direction. So this will be learned later with impulse and momentum. At that time, Ham will explain it brilliantly. Got it? Then learn it then. The only force that changes inertia is impulse. There's only one force. It's really simple. Physics is. Of course, our inertia changes too. Let me give an example. Imagine you have a habit of procrastinating. Sometimes, even if your parents nag you or your friends try to help, nothing works. You know you should study, but you don't. You should do assignments, but you don't. But a time comes when even these students finally study. When is that? Right before the test. A day before a midterm or final, you get the thought, uh-oh, I'd better study, don't you? The thought hits you, I'm in big trouble if this continues. When you're faced with the possibility of a bad grade, you change. Your inertia changes. The point is, when we receive a shock, our inertia can change. Some people experience a huge shock in their life, and then they start living a new life. They get a new habit, one completely different from before. How is that possible? There needs to be a shock. For people too. To change that kind of inertia in people, just saying, hey, study hard won't change it. They need to experience a shock or motivation. Then people change, right? But for an object, just one force of collision, just the force of impact, changes its inertia immediately. Got it? Remember this, force is what changes an object's inertia, and that's precisely why we study mechanics. Next, I'll explain why F equals ma is the most important equation. For now, just keep the second point in mind and we'll cover the other one later. So, where do we apply this concept of inertia? The third point was how to apply the concept of inertia, right? So where is it used? Okay, I've brought a problem related to this. We've learned about the concept of inertia, but many of you might think, isn't that a basic concept? Or is it something we just need to know? So let's see how this is applied to actual problems. This concept of inertia is used to determine the initial velocity, v0. Let's recall an example I've used before. We've practiced drawing graphs a lot, haven't we? Okay, so for our first problem, I've brought in exercise number 11 on one-dimensional motion. A student standing on the ground throws a ball straight up. The ball leaves the student's hand with a speed of 15 meters per second at a height of 2 meters above the ground. In other words, the ball is being thrown upwards from the hand. The problem states that the initial velocity is 15 meters per second. Makes sense, right? So we drew an AT graph. We drew a graph with a constant acceleration of negative 9.8 meters per second squared. And for the VT graph, since the initial velocity is 15 meters per second, it starts from there and takes the form of a straight line decreasing. Got that? And for the ST graph, since the initial position is 2 meters, it will be a concave down parabola that goes up and then comes down. We've practiced drawing graphs a lot, right? The fact that we found the initial velocity, v0, to be 15 meters per second is precisely because of inertia. In other words, the concept of inertia is used when we determine the initial velocity. The moment the ball leaves the hand, it maintains that velocity due to inertia. That's the core concept of inertia. Okay, let's apply this further with exercise number 17. There are also problems where the position, x, is given as a function of time. This is exercise number 17. So, in this case, how can we find the initial velocity? Remember we said that if you differentiate the position function, you get the velocity, v of t, right? I won't solve the problem itself, but I'll explain how to apply inertia. When we differentiate, we get 6t minus 3, right? Now we're going to plug t equals 0 into this. V of 0 is the initial velocity, v0, then you get negative 3. Now the VT graph is a straight line starting at a v0 equals negative 3 with a slope of 6. If we differentiate the velocity once more, we get a constant acceleration of 6, so we can see this is a motion with constant acceleration. Next, the VT graph has an initial velocity, v0 equals negative 3, and since the slope is positive, it becomes a straight line that slopes upward, and the initial position, s0 equals 5. Therefore, the ST graph is concave up parabola. Alright, so this is how we draw the graphs and solve the problem. The initial velocity v0 that we found this way is what is directly related to the concept of inertia. Okay, this is how the concept of inertia is applied to exam problems. You must be familiar with this. Let's practice one more time. It's exercise number 7. Do you remember the supply plane example I showed you before? The scenario involves a plane dropping supplies. It's delivering items to scientists on a glacier from a height of 80 meters. If the plane is flying at a speed of 100 meters per second, at what distance should it drop the package to ensure it reaches the scientists? Let's apply inertia to this one as well. Ultimately, we need to calculate the distance, x. When the plane drops the package, at that instant the package's speed isn't 0, it's 100 meters per second. And why is that? It's precisely because of inertia. Because the plane is flying at 100 meters per second, the package also has a speed of 100 meters per second. When the package is dropped, it becomes a simple problem where the package undergoes motion with constant acceleration in the y direction and motion with constant velocity in the x direction. So you remember how we solved this by separating the graphs, constant velocity, constant acceleration. The motion along the x-axis is one where the speed is maintained at 100 meters per second, right? This is caused by inertia. This initial x velocity, v0x, is a result of inertia. Okay, this is the situation where you use inertia, so you must remember that inertia is used when you're finding the initial speed for drawing graphs or using equations. We just solved that last problem using an equation. Of course, we ultimately solved it by drawing a graph. Now, what's the method we can use to infer the initial speed here? It's inertia. For this problem, it was so easy that we could find the initial speed right away. but later on in the momentum and impulse section it becomes very difficult. You'll have to calculate momentum and impulse, draw a graph, and then find the initial speed from that. It might feel a little difficult for now, but I'm going to explain it all later. I'll do my best to deliver the material well so that you students can master the subject of mechanics. I recommend that you review this video and try to solve the problems on your own. Thanks for watching.